first speaker of the day is Li Cai from Jiaotong-Liverpool Liverpool University in Suzhou, China, right? And he's going to talk about the bar constructions and polyhedral products.
Thank you, Alex. Thank the organizers for the invitation, so I can tell some old stories that I would like to share. So I will start with simplicial things. So I just want to talk about this category. Sometimes people call this simplicial indexing category or ordinal category of numbers. So the objects, they just from 0 to m, they are non-negative integers. And maybe I should use this notation, but this notation is already used a lot, so I don't use it. Okay? And the morphisms are just all the preserving maps of sets. Okay? Okay, this is quite simple category to understand because they are all sets. And so we want to talk about simplicial objects in other category. So a simplicial object in category C is just a contravariant functor from this category to C. So we denote it by okay. So let's give it a name. So let's call it X. So there is a very convenient notation to denote this. That is, we stress on the image of this one. So sometimes we denote where xn is just okay. So this is an object in C. We'll just use this notation. Okay, so it's time to give some interesting examples. In this talk, I just work in this category. Okay? So in this talk, it will be sets. So we have the morphism of just objects, just ordinary sets, and morphism of maps between sets, and also discrete groups. Okay. So this is just ordinary discrete group with group homomorphisms. And also, we consider vector space of a field K. Okay? So these are today's talk. I will just talk about these categories. So usually we call this simplicial set, simplicial groups, and simplicial vector space. Okay? I just don't write it here. Okay, so it's like time to go to an example. Actually, I have mentioned this example before. So we consider Lie group. And we consider all the singular triangles on this group. And these are just continuous or smooth, just say continuous. Okay? So phi is continuous.
C sub n on the right-hand side.
Yes, so this is same, yeah.
About in the parentheses on the right, you need n.
It's small.
Which one? Sorry, in here?
Yeah, in the bracket.
Not this one?
About
Oh, yes, sorry. That's too small. Okay, sorry. Okay, so this is just a set. Okay, so far this is a set. So we just think about the morphism. So I need to explain this one. This one is just the convex hull of the this is in Euclidean space. Okay, so this is just this one. Okay, so it's easy to describe the contravariant functor. So so if you have this f, then you have a map like this. So let's say this is a, okay, so you just send coordinates to this one and take the convex hull. And if you have this one, this is a, then you have this one, okay? So let's write, okay, so this is a contravariant functor. So now it becomes a simplicial set. So now it's simplicial set. And moreover, we can give a group structure because we can take the multiplication of those things on G, because G itself, it has a multiplication, right? So for example, you just take two singular triangles. So then you have the multiplication of G and you get a singular triangle. Okay, so this is in G. So now it becomes a simplicial group. So if you don't have a feeling about simplicial group, you just try to follow this example. I believe that this is one of the most examples that gives us a story between Lie groups and discrete objects. Of course, you can take topological groups. Okay? So there is a geometric realization, and I will talk about it later. Okay, so now I would like to talk about the bar construction. So now I have to suppose that G is a simplicial group. Okay, so that is a contravariant functor from the simplicial indexing category to a discrete group. Okay, so I just use this notation G. That's you can think about this as a singular triangles on some Lie group, or if you want. Okay, so okay. So this bar construction, I need to describe it clearly. It is just a collection of all elements like this. So this is a one-sided bar construction because we don't have anything here. Okay, so this is a, you can think about this singular triangles of dimension I. So this is a set, and we have to think about the morphism. And the morphism is also easy. So you just think about, you need to solve this problem. Okay? When you have a map F here, so how can we describe the elements induced from F? So this is really the interesting part. So you just take the number of the bars, okay? So this is the n bars, and this is a, okay? So you think about F is the map between those bars. So for example, the map will be like this. Okay, so the rule is like this. So put all things, so put the multiplication before to the first position. Okay? So that means, okay, so you just take the multiplication of all elements here. There is some technical thing that they have different dimensions, so you have to use we need something to make them have the same dimension. So this is something technical. I just skip it this time because I mainly work on the algebra, so this part is not that important. But if that's about simplicial groups, we have to make them in the same dimension. Okay. So okay, now if you have the bars like this, you just put the product of all elements here. Okay. If they map to the same, then you just put 1 here. Okay. So between so put the multiplication of all elements, okay, between Fi to this to those in the middle of this one, okay, to those okay, so to here. And if they are the same, you just put 1, okay? So oops, right here. So if so put 1. Okay, so this is the second one. And the last, if you have something here, we have to drop this part out. Okay, so the last one is
Sorry, Lee, I just have a question. Sorry, that when you have that equation, G is in GI, do you mean it's in GN? The last thing, such that G is in GI, WN equals blah, 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 G.
Yeah, so GI is the I-dimensional.
So the ith one, so you have a list of things. So GN would be in big GN, GN minus 1 would be in big GN minus 1. Is that?
Yes, yes.
Oh, okay,
So
okay,
yeah,
thanks.
different dimension. So we need to drop all the things after this one. Okay, so Okay, so let's call this the first. Okay, so this is the second one. Yeah, and this is the third one. Okay, so the picture is quite clear. You think about this map is a map between those bars, and if you have something here, just put it here, and you have two things like this, then you try to put those things here, the multiplication of those things. If they have the same image, you just put one here, and finally you drop this part out. Okay, so this is the way we define this one. Okay, so this is a simplicial set. Okay? So okay, you may feel that it seems that we just need the multiplication of elements. So we can also define it in algebra. Okay? So that A be a graded algebra over a field, let's say. And we need some augmentation here because we want to define the reduced bar construction. So the augmentation means we have a map, which is a map of algebra. Okay, okay, we define a similar object. Exactly in a similar way. Okay, so similarly. On the okay, so because in this definition you just need the multiplication and nothing else, so we can define in a similar way. Okay, now I want to define the classifying space. Okay. So now we define I was going to say this is a oops, excuse me. So this is a simplicial vector space. Okay, so this is a okay. So I didn't talk about grading because that's something with signs involved. So I will, in general, you may think that I'm working over the mod 2 field, then it will be much easier to understand. But in general, just put those signs in the correct place. So I will talk about this later. So, okay. So somehow we need the orbit space of this one. Okay. Okay.
What is G?
So okay, this is a G is this simplicial group. So, okay. Yes, yes. There's a. You see that there's a action on the left, which is a free action. So this is comes from. So this comes from.
Taking a bar times a bar, just putting one alongside the other, does that work?
Yeah, that's actually that's dimension by dimension. Each dimension, this is just the action of the group action on the set. Then just take different dimensions. Okay. So this is because there is a free action of G on this one on the left. Okay. So this comes the free action. So this is also simplicity. Yes, the dimension is G. So they have the same dimension. The action is always in the same dimension. Okay. So if you look at this construction, if you want to understand this W bar G, you just drop this part into the identity element. So you ignore this part, then you get that one. Okay. So this is, and similarly, you can define this one. Just write okay, so this is in this setting, you just observe that there is a this one is actually, so I should write that write a comment here that this is actually a free module, right? So a module. So, okay. So yeah, now I would like to define some differentials on this one to make it a graded algebra. Differential graded algebra. Okay, so that because A is already graded. So in general, that will be different from the grading in A. So that comes from grading in the bar construction. So usually we define it using, actually you can talk about homotopy groups because this is already a simplicial vector space. So, but we have a very nice chain complex that comes from the Morrow chain complex. Yeah, anyway, so we define so you just call this map DI. Okay, so this is a one scheme. Okay, so this one. So the because this is a contravariant functor, so you define this one. Okay. So this is a map from this one to n plus 1 to n. Okay? So we can define a chain a differential. Okay? So D, we define this one. Then this one is a chain complex. Okay, this is actually a free resolution of K. Okay? So I'd like to write some facts. So the first fact is that, okay, so this is we have a fibration. Okay, so the geometric realization of this one is contractible. Okay? So from this one, you can deduce, I think this is the first proof by Ken. And this will imply that this one is a model for, that's right, is a model for BG, okay? So when I should write G, when G is a Lie group. So let's write when G is a Lie group. So this is why we want to consider simplicial group, because this is really a classifying space of something. Okay? And also this one. This is a free resolution. Okay. Okay, next, I'd like to say some result. Why we want this kind of object. So, state the first theorem. So, this is a actually that's also a white hat. So let this be a diagram of monomorphism of simplicial groups. Okay? Then there is a canonical inclusion that you can check easily. So this is a weak homotopy equivalence of simplicial set. Oh, sorry, colimit. Oh, thank you. Okay, so yeah. So this is really a very nice thing that because usually this group in the group category it's an amalgam of two groups that's very large one, but this one is somehow quite small as you think about its topological spaces or simplicial set. Okay, so based on this result, I did a similar thing in the category of homology Hopf algebra. So to skip some technical thing, I just consider this category. Let this one be a monomorphism of connected co-commutative Hopf algebras over K. Then, if you take the reduced bar construction, okay? So I introduce this one? Yeah, okay. So it's a weak equivalence in the category of simplicial vector spaces over K. No. So the proof, I believe, is somehow a similar idea with the previous one, but we need just some algebraic tools. That's quite similar to the proof that why this bar construction is a cyclic. There's a S function that also works in this case. Okay? So let's see some consequences of this one. So that's actually introduced by Stephen, that if we have a flat complex graph, then we can do some induction by cutting it into smaller pieces. So yeah, I just think about the algebraic things, okay, because I have no time to discuss those things in the simplicial group. So okay, so with m vertices, okay? So then you have this one. Just say it's staying. Connected co-commutative Hopf algebras of K. Okay, so let's say homology. Then you have this polyhedral product. That's so this is a. You can really think about this is a topological space, but you just take all the singular triangles on this one. Okay, so this is simplicial vector space. Okay, so this is the bar construction of the graph product of Hopf algebras. Okay, so so let's call this map. Okay, so I'd like to show you one example. So that what does this mean?
So K gamma is the flat complex of gamma?
Yes. So if you take Z mod 2, then you take 3 elements, for example. So this is really an element here, okay? So you just take, because this one is a simplex, so you can take higher dimensional things, but this one you have to take the trivial object. Then you just take the multiplication inside. Of course, I ignore those signs. There is a sign convention. that we have to do every time if you work in the graded category. Okay, so you just take those multiplication. Each entry, then you get this one. Okay, this is on the right-hand side. Okay, so with this one, if you want to compute the classifying space of Hopf algebra, which is a graph product, then you just need to compute something here, which is much easier. You can even use those BBCG technique to do it. So this one looks like the X point K. Okay? So you think about this kind of a polyhedral product. So let me introduce some interesting classes that is available. So you can take the loop homology of those simply connected spaces, okay, Xi. Or you can take the graded quotient, associated graded ring of some group ring, this group ring. We have to take the augmentation ideal. So this is a by this ideal. So let's just take I. Okay, so this is a group ring, and there's augmentation that just send each element to 1. You take the kernel and you take a filtration, you can take the graded ring, then it's a Hopf algebra. Okay, so if you like, you can even take this one as something more complicated, like Stingray algebra or something. But I don't see any application of this case. Okay, so there are interesting cases like this. Okay, so I hope I have time to introduce something I really want to talk about. So I just keep this picture. So let's some applications. Okay. So consider a short exact sequence. Of graded of homology Hopf algebras. So in general, you just need to think about this case. So A is the, so this is the case we are interested in. That's the graph product of those things like this. So this is really the tensor product, and you can define it's the cotensor of these two. Okay, so if you really don't like it, you just take this is a homology of the loop of bjk. Of course, this has to be the k gamma. Okay, this is a so this is the most important example in this story. Okay, so I'd like to consider the change of ring isomorphism. So this is really the very old story that sometimes we want to compute this one using this one. Sometimes we want to compute this one using this one. Okay? So if this is the steamroller algebra, this is generated by SQ1. So this is the calculation done by Novikov to compute the cobordism of the complex manifold with manifold with complex cobordism, I would say. And now we want to do the other direction. We want to use something here to compute this one. Okay? So I need to explain what's this. So first so this is the first observation that you can write A as a free module over A prime and the co-module over A double prime. This is by Miano and then you have this picture that what is the homology of this one? So you take the free resolution. Okay, so take let's take this one. And so this one is computed by the homology of this one. Okay? So this is a free resolution of A prime, and you tensor it over K. The homology gives you this one. Okay? So of course, you can observe that you can cancel these two to get this one. And on the other hand, you can extend this one a bit. Okay, so I mean, this part is another expression for BA. Okay? I just write it as a twisting of this bar and this A. So this is exactly the change of ring homomorphism, because you start from this one, you get free resolution, tensor over K, and you start with the free resolution of A and tensor over A double prime. So you get a common object like this. Okay? So by our previous argument, you can replace this one by a smaller thing. So I'll just state the main theorem. I think I have enough time. So I want to compute the homology of this one. Okay? I would say there's another direction, because I first replaced this by a smaller algebra. So when so there's a this is really another polyhedral product. So this is a polyhedral product of graded chain complex. Okay? So in the category of graded. So this is this will induce an isomorphism. Okay? So I would say this is chain homotopy equivalence. Okay, so what does this look like? This looks like the polyhedral product. Okay, so this looks like this one. You just take the cellular complex of this one, because this is already graded chain complex. Okay, so that's after the Alexander-Whitney map to make it the integrated chain complex. Okay, so then you can compute the homology of this one. Okay, so Moreover, then, this polyhedral product, this is a cyclic. So, each. So this part is something we don't know, but, there is a differential to map this one. So it really looks like this one. So then we have this map. It's a full subcomplex. And take the for some. So when so you just take the homology of this one. This looks like the smash product of AI. Yeah, this is smash product of AI, and this is the homology of the full subcomplex, okay? And then you compute the torsion group of this one. This one is isomorphic to the torsion of A prime. And yeah, I'm already running out of time. I don't have to give you any examples. So in this way, this is actually when this moment angle complex case, this is a result of Villach-Jennings. And this is kind of, in a more general case, you can also do something similar. And the proof is just use what we know about the polyhedral product. Yeah, I don't have time to give you a very explicit example for this one. Okay, so like stop here.